Now, in previous lectures, we've talked about the simple experiment, we've talked about the multiple group experiment, and we've talked about factorial designs. Today, I want to introduce you to the last type of experimental design that we're going to be covering in this course. And that is really a subset of designs that include matched within subjects and mixed designs. But what all these have in common is that in some way or another, we're trying to control the error that's present in most of the other between subjects designs. So what we're going to talk through today is the matched pairs design. And in this first lecture, we'll talk about matched pairs design. And then in the next lecture, we're going to talk about within subjects design. And in particular, we're going to pay attention to why you might want to choose these and what the potential costs are of choosing these. So in the next lecture, in this lecture, we'll talk about the matched pairs design, and then in the last lecture, we'll talk about the within subjects design. So in this lecture for the matched pairs design, I first want to talk through the procedure. How is it that you go about designing a matched pairs experiment? Then we'll talk about what kind of things should you consider when you use the matched pairs design. And finally, we'll briefly mention how you might go about analyzing the data, but we're not going to say much about that. We're going to save data analysis for the second unit of class in which we dive deeper into the statistics. So first, the question that should be on all of your minds, which is, if you have all these great other designs like simple experiment, multiple group experiment, factorial ANOVA, why in the world do we need this one? What was wrong with all of those other designs that a within subjects or a matched pairs design is designed to fix? Well, there's two key issues with all of those other designs, which are under a category that we call between subjects designs. And it's worth pausing for a moment. What do we mean by between subjects? We simply mean that for one experiment, you have a person who's in group 1, and you have another person who's in group 2. And it could just as easily have been that these people were swapped in their places. Any other person can swap with person number 3. Any person in any of these studies could just as easily have been in one group or another. Now, there's a key issue with these designs, in fact, two key issues. And the first one is that these are wasteful. These kind of between subjects designs require a large number of participants. Why do they require a large number of participants? Because, and this is the second issue, they're not powerful. Remember, one of the ways to increase power, statistical power, is to increase our subject size, or sample size. So let's go back to the issue of what power is, because it's worth going back over. Remember, power, when we're talking about it here, statistical power is the ability to find differences between conditions when they actually exist. The ability to detect relationships or to detect differences between conditions when they actually exist. Why do we need power? Well, because oftentimes these kind of treatment effects get hidden, and they get hidden in error. That the more error we have in our study, the less likely we are to detect the effect that our treatment or our manipulation had on one group versus another. Well, why do we have error? Because groups, when we just sort of randomly assign people to one group or another, these groups are always going to be at least a little bit different. That individuals in each treatment group are not likely to be exactly equal to one another before the treatment. And so once we give them the treatment and we measure the differences afterwards, the differences in their dependent variable are likely to be due in part to these pre-existing differences. Okay, so if these are the issues, how do we improve power? Well, the short answer to this is what we want to do is to decrease the effects of error on the differences between groups. Remember, error includes all of those things that make each person in each group a little bit different from one another, right? So when we form our groups, one group may just happen to have a couple people who have had more schooling in their life, or a couple people in the other group who are taller, or who had parents who read to them more often, or who had more experiences outdoors as children. All sorts of ways that we differ. So what we want to do is to try to decrease how much these small differences between people are affecting our differences between groups. How do we do that? Briefly, we want to make our treatment groups more similar to one another. So ideally, the people in group 1, our control group, look as similar as possible to our group 2, our treatment group. Now normally we just do this by randomly assigning and hoping it will balance out, but if we want to do this even more comprehensively, we can use either a matched pairs sample, which is what we're going to talk about in this lecture, or a within groups, or what's sometimes called a repeated measures design, which we'll talk about in the second lecture. So let's get into what is the matched pairs design. What do we do? What's the procedure here? Well, first of all, what we want to do, let's imagine that we have gathered a sample of 12 participants here, which is concerning. That's a small number. So what we would be especially concerned about is, what if we just happen to have a couple people, let's say just these 3 people, who have exceptionally high, let's think about, let's imagine we're going to test the outcomes of a learning intervention on this. So let's say we have a couple people who have exceptionally high IQs. And when we assign them to one group, it may be that not our teaching, but instead their high IQs results in those people scoring higher. So what if we accidentally had all 3 of these people who wound up in the same group, group 1? Well, now, if this group ends up scoring higher, we don't know if it's because our treatment intervention worked or because we randomly had a few people that curved up our sample. So what we want to do is, first of all, to form matched pairs. Okay? So what we're going to do is to find participants who are similar to one another on one or more dimension. So what we may want to do is, maybe if we're concerned that IQ is going to increase people's scores, maybe we want to match people on their IQ. So what we do is we take and we rank order people from the highest IQ to the lowest. And what we're going to do is form these pairs of people who are the most similar to one another on IQ. So subject number 1 is matched with subject number 8. Down here, subject number 4 is matched with subject 11, because these people have, for instance, maybe the lowest IQ. Okay. So once we do this, what we then want to do is to randomly assign one member of each pair to the treatment condition and the other one to the control condition. So here, let's just imagine that the red is the treatment condition, the blue is the control condition. And what we've done is we've randomly assigned, with the flip of a coin, or maybe using a random number chart, assigned one of those participants to be in the treatment and the other one to be in the control condition. Okay, so let's imagine a particular study here. So let's imagine that for our study, we want to measure the effect of tutoring, that's going to be our treatment, versus no tutoring, the control, on people's GPA. But the downside is we only have 10 participants here. What is going to be our biggest concern with only 10 participants? Well, we're likely to make an error. What I want you to think about is, are we likely to make a type 1 error or a type 2 error? Our biggest concern is that we're going to make a type 2 error, that we won't have enough power to actually detect differences if they're there. In other words, our differences are going to be lost in all the within group error. That because we'll only have 5 subjects, half of our sample, in one group, these 5 people are likely to differ from each other in ways that are going to pull one group score up or down. Now the good news is that matching can help us to control this type of error. So I showed you visually how we do this. Let's actually take this with numbers. So let's imagine that we've recruited these individuals and we suspect that IQ is going to have a role on GPA. There's good reason to suspect this because these are 2 variables that are correlated in the general population. So remember, the first stage of matching, Well, the first thing that we're going to do to match them is we want to put similar participants next to one another. So what we're going to do is we're going to first rank order them according to their IQ. So now participant number 6 here has the lowest IQ. Participant number 9 has the highest IQ. So we rank order them from lowest to highest IQ. And now the next thing that we want to do is we want to pair them off one by one. So we take these first 2 people here and they're going to form a pair. Which one is going to go in group 1 versus group 2? Well, to do that, what we want to do is to randomly assign participant number 6 here to either the control group or the intervention group. So we flip a coin and they end up in the control group. And if they're in the control group, the other person then goes into the intervention group. We're going to do the same thing for the next pair. So that's these 2 people right here. And we find with the flip of a coin, this person ends up here, and this person ends up here. And we'll do the same thing with the next group, and the next group, and the next group. Actually, right now we're just putting them into pairs. What still needs to happen, because as you can see right now, actually, the way I've listed this is each one of these 5 always ends up, the first of the pair always ends up in this left column, and the second of the pair always ends up in the right column. In fact, if we just simply took this group and made them group 1, and this group and made them group 2, that's going to cause a problem. In a moment, I'm going to ask you why. So it looks like we have 2 groups of matched participants. Okay, it looks like we have one group right here and one group right here. Seems to be pretty good. Is there anything else that we need to do before we start our experiment? Is there anything wrong with these 2 groups as they are? Well, let's see. If the first subject always went into this category, so the first of the pairs always went into that first category, and the second of the pairs always went into the other category, how are these 2 groups different from one another? And let me show you. Let me actually give you some numbers. Here is the average IQ score of each one of the groups. The average IQ score of this left group is 97. The average IQ score of this right group is 103.8. Why? Well, here, as we rank ordered these people from lowest IQ to highest, even though we came up with pairs, we're always putting the slightly lower IQ person into this left group. And the slightly higher IQ person is going to wind up into this right group. So what we need to do now is to not let these groups stay groups. What we need to do is to randomly assign one person in each one of these pairs to treatment versus a control group. So now we flip our coin, and subject number 6 on the coin flip goes into the control group. So we put their partner, participant number 8, into the treatment group. We do the same thing for the second pair. Here, this participant happens to go into the treatment group. Again, remember in this first one, that person went into the control group, so it's already starting to balance out a little bit. And we do the same thing for each one. Sometimes the higher IQ person goes into the treatment, sometimes into the control group. Now, what we're going to do is to take one more look, and now what we want to do is to measure the outcomes. Now that we have these participants in each group, we are going to give one group the treatment, the tutoring, and we're going to give the other group a control, no tutoring. Okay? And our outcome is going to be GPA. So this is going to be the chart of our GPAs. So let's imagine for a moment that our treatment does nothing. I want us to imagine a circumstance in which our treatment has done nothing. And the only thing determining people's GPA is their IQ. So why go through all this trouble? Is this any better than just simply randomly assigning participants? Because what we're going to end up with is a group of people, and you see some with low GPAs, some with high GPAs, some with low, some with high in each one. Well, let's assume that the treatment did nothing and that the GPA is correlated with IQ. Here, these GPAs that we have here are correlated with their IQs at a level of 0.96. So I simply came up with a list of GPAs that correlated with these participants' IQs at 0.96. Here, the GPA for the treatment is 2.42. In a perfectly matched setting in which we have identical groups, these two mean scores should be identical. Here, the mean for the treatment is a GPA of 2.42, and the control is 2.48. Not bad. It's not perfect, but it's not bad. Let's take a look at what this would have looked like if we had just, instead of matching pairs, if we had randomly assigned individuals to groups. So here what I've done is I've taken and just, instead of matching them together and pairing them off, I've just randomly assigned person number 1 through 10 using a random number generator to either the treatment or the control group. And what we find here is the mean of the treatment group is 2.34, and the mean of the control group is 2.56. Remember, assuming that our experiment did nothing, our measure of error is how far apart these numbers are. And here what we found is the difference between these two numbers is almost 4 times as big as it was over here. In other words, our matching reduced the variability between groups due to error by 75%. Because we know the treatment did nothing, this is all error, 4 times as much error. So how does this help us in the long run? Well, IQ we know is correlated with GPA. But if you're doing an experiment on, let's say, happiness, maybe you know that extroversion is correlated with happiness. So you want to pre-measure people on their extroversion levels. But for us, if we know that IQ is correlated with GPA, and we're hoping to influence or manipulate people's GPA by giving them tutoring, what we want to do is, by matching them on IQ, we make sure that our groups are at least relatively equal on GPA without the treatment. Statistically speaking, what we're saying is we reduce the chances that these two groups are going to differ by chance alone. So when we're trying to match participants like this, there's a few different considerations we'd want to think about. First, we need to find an effective matching variable. So if we don't know what predicts GPA, we're not going to be able to match our participants at all. Or if we know what predicts GPA, but we can't measure it, we're stuck. With respect to why use it, power is a major reason to use this match pairs design. It really increases power by decreasing the ways in which random errors, random differences between people are affecting group scores. For external validity, the advantage is we don't have to restrict our participant population. One of the other ways that we can reduce error between groups is only looking at very similar people. So for instance, Kendra, my wife, for her doctoral dissertation, she looked at individuals with agenesis of the corpus callosum. And so what they had to do, because it's an unusual medical population, what they had to try to do is to find people with similar IQ scores to these individuals. It was really challenging to do that. One of the ways that you can sort of, in an experimental design, if you're trying to get 2 people, let's say we wanted to improve GPA and we wanted to take out random variations in IQ, well, one of the things we could do is only accept into our experiment people who had IQs of exactly 100 or between 100 and 105. Now it works because we've reduced between group variance. We've made those groups very similar. The downside is we've restricted our population, because even if tutoring helps out people with IQs between 100 and 105, what we don't know is how that would work out for people between 110 and 120 or 120, 130. The downside to matching is that the results may not generalize to participants who haven't done the matching task. Now, this is a little bit counterintuitive, so I want to talk you through this. So one of the things that we've done in our study in order to match our participants is we've had to, let me actually even go back a little bit further, is we've had to measure their IQ scores before we expose them to our treatment. So all of our participants have first taken an IQ test and then have done the treatment. What we know is, if we find significant results, we know that our treatment works for these people. What we don't know is whether it's the treatment that did it or whether it's the treatment plus having taken an IQ test. Maybe our tutoring only works when people have taken an IQ test first and they're made aware of their gaps in their knowledge. So now you take an IQ test and all of a sudden it makes you nervous about what you know. So then when you get tutoring, you take a lot out of the process. In other words, again, we don't know if our results would generalize to participants who haven't done the matching task, in this case, the IQ test. And similar to this, our construct validity may be weakened because the matching process may tip off participants about the hypothesis. So if they take an IQ test to begin with, it may tip people off when they then receive tutoring to say, oh, I think these guys are going to want to know my scores on that exam. And so people may work at a different level. Remember how we've talked about the ways in which the placebo effect sometimes makes people perform differently. And we talked about the workers in the electric plant, the Hawthorne effect, in which people who are receiving attention can kind of guess what it is that they should be doing differently when they do it. So all that to say, matching, one of the downsides is that construct validity may be weakened. Here's my question for you, and we're going to talk about this in class. I want you to imagine this. An investigator wants to find out whether hearing jokes will allow a person to persevere longer on a frustrating task. So to increase power, the researcher matches participants based on their reaction to an initial frustrating task. In other words, they make all these people frustrated to begin with, and they find out what their reaction is. Then they take people who had really strong reactions and they match them. They put one in one group and one in another group. Of the 30 original participants, 5 people quit the study after going through the frustration pretest. Okay, so this is the circumstance. They want to find out whether hearing jokes allow a person to persevere longer, but they only have a small sample, so they match them by giving them a frustration task to begin with and seeing how they respond. They then use that to match people in the 2 groups, but they have 5 people quit the study after they go through the frustration pretest. Here's my question for you, and we're going to talk about it in class. Beyond the ethical problems, what problems are there in using a matched pairs design in this situation? Obviously, there's the ethical problem of frustrating people, making them mad, but experimentally, validity-wise, what are some of the issues with using this specific form of a matched pairs design? Write your answer in the box below. We're going to talk about it in class. Okay, briefly, just to end with, when we analyze the data from a matched pairs design, we're not going to use the typical, what's called between subjects t-test. And this is because our observations are not independent of one another. Why are they not independent? Well, because this person's, our observed score for them is actually dependent on this person. They are matched with one another. In other words, these people have something in common, which are that they are the lowest IQ. And so what we're going to do is we're going to use a specific kind of t-test that looks at this person versus this person and tests the difference, so to speak, between their scores, and looks at this person and measures the difference between their scores. Okay, so what this is called is a dependent t-test. And it's going to measure the differences between pairs. And in the end, it's the standard error of these differences that's going to be used as the error term. Okay, that's it for this lecture. The next lecture, we're going to talk about within subjects or repeated measures designs and why they are even better than the matched pairs design.